Welcome to the day 4 of 5th week. Yesterday we learned about the relation between the group theory and quantum mechanics a little bit. So today we will start with a concept, the concept of the direct product. Okay, we introduced that in I think a couple of classes ago, but here we are going to have some detail about that. So if we take R as an operation in the symmetry group of a molecule, and x1, x2 up to say xm and beyond, and y1, y2 up to yn are two sets of functions which are the basis for representation of the group. In that case, what we can write is given here. So I can express this operation, R on xi as the sum of the contributions of each xi's. So in terms of this coefficient small x ji or small y lk, right? So I can write that, and also we can have this particular relation. Okay, so which tells you when you combined this basis functions x and y's, and then operate the symmetry operation R on that, and you get the result as this one. Okay, which is really not much different from this individual ones, right? If you look at that, so this which we are talking about is the combination of the basis functions, two different sets of basis functions, essentially two basis sets, and then combine them and then operate the symmetry operation on that, and you get the result. So therefore the set of the function, this xi yk, they are called the direct product of xi and yk, also forms a basis for the representation of the group. It is very similar to the example that we gave in the last class, where you had this wave function which acts as an eigenfunction. Now when you operate symmetry operation on that, so you get R psi I, that R psi I also acts as an eigenfunction. So here this is just an analogy. You have the individual basis functions as xi's and yi's or yk's. When you combine them, okay, one to one, then the set that you get, that also act as a basis set for the representation of the same point group. Now the characters of the representation of a direct product are equal to the products of the characters of the representation based on the individual sets of functions. Okay, so the example is given here below. Okay, so we have taken an example of a point group C4V, and this is the character table for the point group C4V. Now you have a direct product. So generally direct product are written like A1 and A2. Okay, so if you are having a direct product between this one, so you normally write it like this, okay, or simply like this. Okay. Now when you have the direct product here, so what you have one to one product between the characters corresponding to the two different irreducible representation and a particular one symmetry operation. So for example, if we want to have a direct product of A1 and A2, then I will have the product of this character and this character, both of which correspond to the same symmetry operation E, but we will not have any crosstalk between this and this. Okay, so after having this one to one product, we get another representation. So we get this here. So this is very easily it can be seen that 1 into minus 1 gives minus 1, again 1 minus 1 gives minus 1. All right, and if you have any direct product combining one particular irreducible representation and the E representation, then you get the corresponding direct product as it is given here, like B1 and E, the direct product gives you this representation. All right. Now you can take any particular point group, you can find the character table, and then you can combine any two irreducible representation by doing that direct product of them. Okay. Now you may ask, okay, why do I need this direct product? Okay. In the previous class we have seen one example of having the direct product. Now there are much more important role that direct product actually plays. So let's see how these direct products are used actually. So if we have an integral of the product of two functions, for example fa and fb, and we integrate over all the coordinates denoted by tau, this integral will yield 0 until and unless this until and unless the integrand is invariant under all the symmetry operations of the point group to which the molecule belongs to. Also it will give 0 unless some term in this integral, if it can be expressed as a sum of terms, that remains invariant. Okay. So in a nutshell, if we have to talk in terms of group theory and symmetry, what we can say is following: that representation of a direct product, if we denote it as gamma AB, then gamma AB will contain the totally symmetric representation only if the irreducible gamma A equal to the irreducible representation gamma B. Okay. So we can prove that quite easily. How we can prove that? So let's do this. So we are familiar with this this particular equation, which gives you the number of times an irreducible representation will appear in a given representation that one can form. So that is given by chi reducible of any given R and the particular irreducible representation that we are concerned with, right? This one we know. Now what we are talking about here, that is the this reducible representation. We are talking about the representation that is formed by the direct product of two irreducible representation. Now we have been talking about this particular integral, that integral FAB over d tau, that will vanish until unless the total integrand is invariant. So what do you mean by this word invariant here? That means it's whatever symmetry operations you operate, it's not going to change. So all the time it will give you a +1 as character, right? Now these functions can be and wave function, right? And wave functions, they form the basis of irreducible representation. So ultimately it boils down to the property of the irreducible representation. So therefore I can think of this FA into FB to be the direct product of two irreducible representation, right? So the result of the direct product, if it gives you the totally symmetric IR, then only this integral will survive. Otherwise, if it is not symmetric, then this integral over all the coordinates, it will vanish, right? That is well understood. Now, what we wanted to prove here, that in a direct product, the totally symmetric representation will occur. Like if I have two representations, say A and B, and the representation that we get after doing the direct product, as gamma AB, it will contain total symmetric IR only if gamma A equals to gamma B, where gamma A and gamma B are two irreducible representations, and that is what we are going to show here. So, this I represents one of this gamma A, or one of the IRs of the point group, and here particularly we are interested in a particular IR which is totally symmetric IR, and totally symmetric IR is always represented by A1. So, if I replace this I by chi 1, and here I write A1, meaning that I want to find out whether this A1, that is the number of times the total symmetric IR will occur in this representation, which in our case say AB, right, that is the direct product representation that we get. So, how many times this A1 symmetry, that is the total symmetric IR, will occur in this one, correct. Now, this is a one dimensional irreducible representation, so I can write here clearly 1, fine. So, once I am talking about the totally symmetric IR for which all the characters are +1, then I can simply write this one as 1 upon H sum over all the R chi A B of R. Now, by definition of direct product, chi A B is equal to the product of the characters of representation A and representation B, correct. So, if I replace that here, then what I get is this. Now, if I look at this from the great orthogonality theorem, I can easily say that this will survive, this whole thing will be non-zero only when A equals to B, correct. So, this means delta AB, right. So, this is equals to 1 when A equals to B, and that is what exactly we said, that if A and B are same, that means if the direct product is done between the same irreducible representation, then only the totally symmetric irreducible representation will occur, or will be contained within that direct product, otherwise it will not. And therefore, if I have a represent, if I have an integrand where two functions which transforms as two irreducible representation of the point group, they will survive only when those two functions correspond to the same irreducible representation, otherwise they will not survive. Okay. Where this property is used? This is used when we try to find out the energy elements of any given molecule, or we want to find out about the spectral transition probability, and we will have a look at those things right now. So, and what is an energy integral? Energy integral we can easily find out, because you know about the Schrodinger equation. So, you have say H psi j equals to E j psi j, right. Now, if you multiply both sides by psi I, okay, and then you integrate. So E being a constant, I can easily shuffle this one. So what I can do is I can write psi ij and bring E here. Now if I integrate over all the space, so what I can have is psi I fine, that's my energy. So this particular thing is called the energy element of the system. So and it is also known as energy integral. So this will be non-zero if and only if this psi I and psi j, they belong to the same irreducible representation. Why so? Because I know that this Hamiltonian operator, that doesn't change the symmetry properties of a molecule, right? So H commutes with any symmetry operation that we have already seen. What does that mean? That H is invariant to any symmetry operation. Again, what do I mean by that? That means that H, which is an energy operator, is the basis for the totally symmetric irreducible representation, right? So if this belongs to totally symmetric irreducible representation, then it must be A1, correct? Now you multiply anything with A1 will give you back the same irreducible representation, because you are just multiplying with plus 1. So therefore, if this integral has to survive, what I need to have is that this two product, that is the direct product of psi I and psi j, meaning the direct product of the irreducible representation to which psi I and psi j belongs to, they should either yield totally symmetric IR or should contain the totally symmetric IR. Okay, so just now we have seen here that the totally symmetric IR will be contained within the direct product representation only if the two IRs that we are combining are equal. Fine. So that means here that IR to which the psi I belongs to must be the same IR to which psi j belongs to. Okay. So that's what is stated here. Now the next important thing that we will be talking about is the spectral transition probability, and we will see how this direct product helps us in getting this spectral transition probability. So we are already in the the application part in some way. So for any transition between two states, okay, it can be an electronic state, vibrational state, or any other state. So if the state, ground state and the excited state, if we are describing them by two wave functions psi I and psi j, then the intensity of this transition, which is denoted as this I, is given by this integral. Okay, so this is called transition moment integral. Now the intensity of this transition is directly proportional to this integral, and this mu here, which is acting as an operator, this is a transition moment operator. Okay, so this can be different way this operator can work. For example, it can be electric dipole operator, it can be magnetic dipole operator, it can be a magnetic quadruple or higher order multiple, it can be a polarizability tensor and so on. So the nature of mu can vary, but the most common form of mu in the spectroscopy that we often use is the electric dipole, and we will also restrict ourselves in our all the discussion even in the following weeks to this particularly electric dipole allowed transitions. So, where mu will have the form as given here. So, mu will be a dipole moment operator, and a dipole moment is given by the charge multiplied with the distance. So, for any given given particle, the distance is quantified by 3 Cartesian coordinates, so x, y, and z. So, therefore, we can express mu as the sum of this charge distance product in 3 different directions, x, y, and z, as given here. Okay. And we can have many particles in the system. So, for each particle I can have this charge distance product for each coordinate, and then we can sum it over all the particles. Okay. So, that is given here. So, this is a beauty of this orthogonal coordinate system x, y, z. Why so? Because I can separate the different contributions of mu along x and y and z directions, okay, and express them just by sum of the 3 coordinates, and they are not dependent on each other. So, I can separate them out very easily as shown here in this particular equation. So, when I can separate different contributions of mu, that is mu x, mu y, and mu z, I can split the transition moment integral also into 3 different integral as shown here. So, I can have an integral which is dependent on the x coordinate, and then y coordinate and z coordinate. Fine. Now, one thing you notice here that we are not using this this charge values here, because that is a constant, and that does not change the the value of integral, right. So, that will be just a multiplication after you solve the integral. So, now if one or more integral survives, then what we say is that transition from psi I to psi j is allowed, and is allowed in those particular direction, meaning like suppose the integral involving x is non-zero, but other 2 integrals are 0, then we say that the transition is x polarized. Or suppose if it is surviving for integral involving x and y, but the integral results 0 for the z axis, then we say the transition is polarized in the xy plane. So, that means if we come with a light, okay, which will cause the transition from one state to another, if we have the electric field vectors of this light polarized in those directions, then only we will have the transition. Okay. So, we can give you a very quick example, and then we can close this section and move on to the next part of the symmetry adapter linear combination. So, if we look at the example of a particular molecule which is dimolybdenum complex of a ligand which is like simple as chloride. So, for this particular molecule whose structure is shown here, their highest occupied molecular orbital or HOMO is a delta type orbital, and the lowest unoccupied molecular orbital or LUMO is a delta star type orbital. You don't have to worry about what is delta star and delta because we are giving the detailed picture of the orbitals for this HOMO and LUMO explicitly here. Okay, so this is the HOMO part, and this is the LUMO part. All right. Now, if we have to find out whether the transition from HOMO to LUMO is allowed in this particular case, and if it is allowed, then in which particular direction, then what we have to do, we have to determine the irreducible representation to which these two orbitals delta and delta star belong to. Now, since we have the detailed picture of delta and delta star, we can find out the irreducible representation to which this molecule belongs to. So, what we have to do, we have to operate all the symmetry operations for this particular point group to which this molecule belongs to, operate on this HOMO and LUMO and get the representation. So, the molecule belongs to D4H point group. Okay. So, if you are not convinced here, then I will request you to go back to the second week of tutorial, second week of this lecture, and learn a little bit more about this point group analysis. So, this molecule is having D4 symmetry, D4H symmetry. So, once we operate all the symmetry operations on these two orbitals delta and delta star, we see that we get representations as this. All right. Now, what you have to do, we have to consult the character table of D4H point group. So, any standard book will give you the character table of all the point groups. So, here we are giving you the character table of D4H. So, now if you compare this representation with this character table as a whole, then you can find out which irreducible representation delta belongs to and to which representation the delta star orbital belongs. All right. So, that is given here. So, the delta belongs to B1G and delta star belongs to P2U symmetries. So, we have got the irreducible representations to which these two orbitals which form HOMO and LUMO they belong to. So, now what we have to do? Now, we have to look at the transition moment integral. Okay. So, that is given here, and here again you notice that we are not bothered about the charge because that is not going to alter the fate of the transition, correct. So, we will be so this one is this is essentially psi delta and this one is psi delta star. All right. So, this integral we can split in three different integrals involving x, y and z separately. Now, this what we have to do, we have to find out to which irreducible representation this individual x or y or z coordinates belong to, or in other words, for which IR this x or y or z form the base. Okay. So, if we look at the character table, we can easily locate that. So, you can see that z, so z forms the basis for A to U. So, I can say the z transforms as A to U, and you can see x, y they transform together as the irreducible representation EU. All right. So, we got all the information that we need to solve the integral, right. So, here, so we have already find that z vector transforms as A to U and x and y together transform according to EU. So, what we have to do? We have to replace this this delta and delta star by their respective irreducible representation, and also we have to replace the x, y and z by their respective irreducible representations. So then we are left with these two different cases of direct products. And now whichever direct product yields the totally symmetric irreducible representation, that will survive. Now here in this particular case, this x and y forms together. Okay, so this particular representation, it deals with the x and y together, and while this one, it deals with the z polarization. And once you solve it, which is very easy, and you can figure out that first one, it gives you A1G, the totally symmetric IR, while the other one is not the totally symmetric IR. So clearly the integral involving z will survive, while the other one will vanish. That means our this HOMO to LUMO transition is allowed overall, but it's allowed in the z direction, and it is forbidden in the xy plane. Okay, so we also call that the transition is z polarized. All right. So here we showed that how this concept of direct product can be very much useful to have the have an idea about the transition probabilities and intensity of any given transition. Okay, knowing the irreducible, knowing the properties of direct product involving the irreducible representation of any symmetry point group. So we will stop here today, and I thank you for your attention.